rewrite system. And people who know my work will know that I've been talking about a universal rewrite system for a long time. So I think such a system determines everything in nature. It's a repeating fractal kind, relatively simple mathematics. I think of it visually a bit like a Mandelbrot set, where you keep seeing the same pattern and at different sizes, and it's always the same pattern. So the thing is, can we detect it, and can we show its operations in nature? And is there some kind of universal unit, as it were, something or other that we can identify? Physics is a large subject. How much leads to something fundamental? Well, to find that out, we need to use two other subjects. We need to use philosophy and mathematics. And in my opinion, philosophy is the more important of the two, though mathematics is also tremendously important. Richard Feynman said a lot of negative things about philosophy, and other people have, but it's very much the basis of physics. Without philosophy, we wouldn't have physics. So we've got to get our philosophy in order before we can do our physics. And we need to know how fundamental ideas should be constructed. You can't just pluck ideas arbitrarily out of the air and hope they work. They don't. I'll tell you where I'm going to start. I'm going to start from zero. This is a system with no characteristics. That's what I mean by zero. And it doesn't have an explanation. It's not the beginning, it's not the end, it's just there. There's nothing. And obviously mathematics is tremendously important. But I say philosophy must precede mathematics. We don't have a completely free choice. And I think Dennis said something like that about his choices of algebras or systems. Physics, quite honestly, has made no fundamental progress since the Standard Model in 1973. Absolutely none whatsoever. And why is that? And I think it's because it's rejected the philosophy. And it's attempted to impose mathematical structures. And these just push the problems down the line. So you just get bigger and bigger, more complicated mathematics, and it's useless. And this is a way of avoiding the real explanations. You just make it more complicated. Anybody can do that. You can always prove any thesis you want as long as you make enough complicated assumptions. So pure empiricism doesn't lead us to the answer. We've done fantastic experiments in those periods, and yet we've not got any new ideas to solve it. So we have to look at it a different way. And to me, there's one great guide, always, and this is Newton. Because Newton, I'm not interested in the actual discoveries he made, I'm interested in the methodology. Because he made an enormous breakthrough. He said physics is about abstract categories, which we call parameters. And they're connected by simple mathematical laws. And at the same time, he developed the mathematical structures which would apply to them, particularly calculus and basic vector theory. And I don't think the procedure's ever been bettered. You can't do better than that. Many physicists have tried to improve on Newton, so-called, leaving out the philosophy. Now, I quote Bertrand Russell here. I'm not as good at impersonating him as Alan Bennett was, but however, he said there's a special place in hell reserved for philosophers who've tried to refute Hume. And in that I would include the governance of Edinburgh University for cancelling him. Newton says there's an equally special place, perhaps an even more special place for physicists who tried to refute Newton. He said there are quantities in physics, mass, length, time, space, we call it now, in dimensions nowadays, which were brought in the 19th century, which don't resolve into anything simpler. And the one he added to the age-old space and time was mass. That was a quantity of the same order. And this is odd because it seems to be something substance, something you can grasp hold of. Doesn't seem to be abstract. But the fact that he created an abstract quantity made a big difference to physics, because causality had to be it added to observational description, and kinematics had to be replaced by dynamics. Now here, mass initially is discrete mass, but I will always think of it in terms of energy or dynamic mass. And I believe in relativistic mass, whatever anyone else says. And Newton, in fact, also believed in some sort of dynamic version of mass, but that's another issue. Now, at the particle level, discrete mass, as I mentioned during discussion, is in fact dynamic as well, because it comes from Zitterbewegung, which is a dynamic process. A dynamic quantum process produces what we think of as solid mass. And if you look at the masses of quarks and protons, for example, protons seem to have a solid mass, but we know it comes from the dynamics of the quarks inside the proton.
In a sentence, what's Zitterbewegung?
I'm sorry?
In a sentence, what does Zitterbewegung mean for
a jittery motion is what it literally means.
Mm.
But it's the switching between one spin state and another, and in and out of vacuum and so on. I can explain it later. Mm. But Newton's mass is also abstract because it's part of a set of composite quantities and powers of them. And these have mathematical properties. In fact, we know that space has vector properties and differentials, and for space and time, that they're not just quantities. You've got to do differentials of them. They're calculus quantities. And we also need time squared. We can't do anything without time squared. We have to have acceleration. We can't use velocity. We've got to get time squared. It doesn't mean anything without. And we know now, though, it's because time's imaginary. We know time's an imaginary quantity, so that's why we have to use time squared. So Newton also simultaneously pursued the mathematical studies relating to these physical notions. He actually pursued the mathematics of space and time, and that's how he developed his calculus through, if you look at his early papers on calculus, they're all about to resolve problems by motion, space and time, and stuff like that. Now, if we take the most abstract stance we can, we're going to involve philosophical ideas, whether we like it or not. And one of Newton's specific contributions is a version of the zeroing principle. He has a composite quantity force which has to be zero in a conserved system. So he's got a zeroing principle, an extreme principle, an extremum principle. That's his third law of motion. So this is the principle of zero force. This led to many other extremum principles involving similar quantities, energy and action in particular, various mathematical successors. Some of them were done by Newton, some by his successors. Maupertuis, Euler, Lagrange and Hamilton developed all these ideas. The conservation laws of energy, momentum and angular momentum, and the zeroing of the can I just get rid of that thing so it doesn't affect my slides, because some of them do go to the model. Oh, never mind, I won't bother.
I think it's good to see.
Yeah, thanks. Yeah.
Forward.
Yeah, that's the slide I was just looking at. And eventually, one of the great principles is the principle of least action, which isn't correctly named because it's the principle of extreme, change of action, as it were. It's not the principle of least, it could be the principle of most, or even the principle of stationariness. But it's always called the principle of least action. So the idea of conservation emerges from this. Mass is specifically stated as a conserved quantity, and then all the quantities which include mass are conserved, or in some way have an extremum principle. And that's what happens. So the definition of force leads to the idea that a system requires a combination of these. You can't just have these abstract quantities and treat them separately. You've got to combine them in some way, mathematically. And another thing that creeps in here is symmetry. Because that's true of the third law of motion, it's a symmetrical law. It's also true of Newton's law of gravitation. And it plays a big part in that. Kant proposed that the inverse square law of the force is an expression of the spherical symmetry around a point source. And I might say something more about that later, because I have a quantum version of that. Now, Newtonian mechanics, we often treat it when we teach it as simple, you know, interaction between one particle and another and that kind of thing. But in fact, there's a huge section of the Principia, propositions 39 to 42 of Book 1, which does away with that approach. And after he discovered this new approach, he didn't use his old approach anymore, that we do in teaching. And these treat a whole system using what we would now call an energy approach. He never uses the word energy, but they are energy equations. And the great Newton scholars like I.B. Bernard Cohen and so on discovered this, and it wasn't him who discovered it, but he promoted this idea. And this is another significant development in physics because it moves away from the specific to the abstract, the generalized. And so we have the principle of least action follows from Newton. It follows afterwards. It's about 50 or 60 years after his development of these ideas. And the use of the Lagrangian and Hamiltonian functions, which is what all physics does now. In addition to the development of the Laplacian operator, del, and so you can express this inverse square of gravity simply by del squared phi equals 0, phi being the potential. And so we're moving towards using operators rather than parameters. So the parameters transform themselves into a kind of operator thing, without, of course, affecting anything fundamental. Now, of course, we've moved a long way beyond classical mechanics and even gravity. So there was a huge development in the 18th century of electrostatic, electromagnetism, optics, which eventually led to Maxwell's equations in the 1860s. And also to special relativity. Now, I'll say something about special relativity here. This is about the combination of space and time at the fundamental level. It's got nothing to do with all that nonsense about relativity, simultaneity, and no macroscopic measurements. They don't tell you what it's really about. It's really about a combination of space and time mathematically. It's not really, all these are just effects, they're not the explanation of it. And unfortunately we teach it using the effects rather than the true meaning, which is a mathematical connection.
Measurement effects, right?
Yeah, measurement effects, peculiar things. And a lot of those explanations are not very good. I don't think it's correctly applied to gravity. It's applied correctly to gravity plus inertia, but not to gravity, in my view. I don't think gravity at all is at the speed of light. I think it's inertia that is. And the speed of light occurring in gravitational waves and all that is from the inertial contribution. I'll say more about that later. The connection requires the recognition now that time is a pseudo-scalar or imaginary quantity. And then, if you do vector theory in the modern way, which most people don't do, which is to start with quaternions and then extend them into vectors, then you will see that imaginary quantities are a fundamental part of vector theory. They are anyway because pseudo-scalars are imaginary quantities, the product of three vectors, and pseudo-vectors are imaginary vectors. We'll say more about that. It makes pseudo-scalars important in vector theory. You're going to get I coming up in vector theory. We'll see later that the space-time connection isn't specially favoured. It's important, but it's not the only one. There are other connections at the same time. It's a simultaneous connection of several things. Now, we know that Maxwell's equations were brilliantly reduced all of electromagnetism and optics into four equations, which are basically the inverse square law for electrostatic charge and what we would now call relativity, and we could do the whole lot just using those two principles, and we don't even need the four equations, they're just how it works out. But you need this new abstract parameter charge on the same level as mass, and this is an inverse square law, which is called the Coulomb's law, and it also has a Laplace equation, same as gravity does. But there are good reasons, I'm not going to go into them now, but I've done them many times over, for thinking charge with both positive and negative values is really an imaginary quantity like time. But it isn't a pseudo-scalar quantity, as we'll see. So the 20th century brings in new concepts, new laws, new forces, strong and weak. And there's something similar about those to electromagnetism, and each has a Coulomb component, as well as another one. So the strong and weak have Coulomb component plus another one. And they're both different, they're different to each other, and the electromagnetism doesn't have an extra component. So there's something that makes them similar, all the forces similar, is Coulomb component. Now we're going to have to make a huge guess here. At this point we're going to have to make a big guess. And at some point long ago in the past I made this guess. And if your guess works, then great, you start cooking by gas. But if it doesn't work, then you throw it out. It's simple. There's nothing wrong with making a guess, but we're making a guess now. We're going to assume that the electric strong and weak have all got imaginary sources, and we can guess that charge is really represented by an imaginary three-dimensional quantity, which we call a quaternion. And that the real part of the quaternion is mass, and that's why you get this similarity. Why are they different? Well, we'll see why they're different, because mathematics forces us to break the symmetry between them. Now quaternions, and they're in vector algebra, they've been in vector algebra ever since vector algebra was invented, and they're called pseudo-vectors. The cross product of two vectors is a pseudo-vector. Angular momentum is a pseudo-vector. It's actually a quaternion. It's an imaginary vector. So we're using quaternions, but people are shunning the word, but they are quaternions. So vectors in effect complexify quaternions, and quaternions are complexified vectors. That you just multiply them by I and switch between them, with plus or minuses and so on. So if we say quaternion algebra is correctly applied to charge, then we got pseudo-vector, we got pseudo-scalar for time, we've got vector for space, and we've got scalar for mass. So we got all the parts of the same algebra. And if we look at these algebras, then this introduces so-called physical characteristics of the parameters. Vectors and quaternions are both three-dimensional. Now what does three-dimensional mean? It doesn't really mean dimensional, it means anti-commutative. Because if you've got anti-commutative, it means AB equals minus BA. So vectors and quaternions are both anti-commutative. And once you do that, then you have to introduce dimensions, because there's no other way of doing it. And the minimum number is 3. And in fact the only number is 3, because if you push it any higher, you have to make it 7, and it's also got weird algebraic properties which don't fit into physics, as I mentioned. So you're kind of creating little discrete three-dimensional systems once you introduce vectors, once you introduce three-dimensional objects. And in fact, if you look at nature, that's where all of its discreteness comes from, these things. There is no discreteness in nature other than from three-dimensional quantities. Space is discrete in a special way, it's discrete in a non-conserved way. It's the Robinson method of doing differentiation, etc. Time is not discrete, it's continuous, and it's a scalar, pseudo-scalar. Mass is continuous because it's energy. It's not discrete mass. Discrete mass comes from something else. So the real imaginary distinction is obvious. And if we got three distinctions between these sets of parameters. We've got continuous and discrete, or dimensional and non-dimensional. We've got real and imaginary, that's an easy one. And then we've got, finally, conserved and not conserved. And that's the divisions, the things that separate the parameters. And this is the one I found most difficult. Conservation appears to be associated with parameters that don't have a pseudo-scalar component. Whereas non-conservation, they have a pseudo. So vectors, the vector quantities aren't conserved, time isn't conserved, that's space, time isn't conserved, and they've both got an I in them, and a pseudo-scalar I. Now, charge and mass don't have that, and they are conserved. I've still got to find a proper proof for that, but the general idea is as far as I can see, is that. Now, if our quaternion representation of charge is true, then we're going to get a fantastically beautiful symmetry between the four parameters. Mass as a group of order 4, Klein 4 group, and I call that kind of periodic table. The exactness of the properties and anti-properties indicates the total structure maintained. If every property is countered by an anti-property, then the whole will be characterless and zero. And I've tested this over a long period, and I've found that apart from the symmetry breaking between the three charges, there isn't anything that goes against it. And it's actually brought up new things. New things. I thought of an extension of Noether's theorem, which seems to work very well. And that's the group table. That says anti-commutative at the bottom, and that's what they are. And continuous is the same as commutative, and discrete is the same as anti-commutative. So that's the group table. You can see it's a symmetry, and it's actually Klein 4 group. And that's the group table. There's some sub-symmetries in there, two major ones: duality, C2, and anti-commutativity, which is 3 dimensions, based on 2 and 3. And 2 and 3 are the most fundamental numbers in nature. You find them everywhere. 2 this, 3 that. And it's always the same 2 and it's always the same 3, just in different guises. There's also a dual group, and the easiest way to create the dual group is to, can I go back? Is to switch the, you can switch any parameter, but the easiest one to switch is the real and imaginary one. Sorry, I need the previous slide. In the middle, the real and imaginary one. So if we make mass imaginary and time real, and this, you see this in certain representations of quantum mechanics. For example, in the Dirac equation, you've actually switched the real and imaginary around. And
Wick rotation does that as well, I think.
Does it?
I think there's a technique called wick rotation. You can rotate it to imagine.
So we switch the real and imaginary round, and we get a dual group, which is also a group of order 4. So, so you can represent dual group and group in the same representation. That's a nice one. That's the colour representation. You've got 3 properties, 3 colours, 3 anti-colours, and they all add up to white, of course. I shouldn't say that, of course. And that's the cubical representation, where the red are the real the group, and the cyan is the dual group. And this one is actually very useful because you can translate it to a Boolean cube, and you can do things on it. You know, Boolean cube with 0, 0, 1, and so on. This is the tetrahedral representation, and you can either use faces or vertices as the 4 points, and you can switch them round. And of course you can switch the tetrahedron round, because you can invert a tetrahedron into another tetrahedron.
It's probably another reflection of why 3 dimensions is kind of
it's special.
Special, yeah,
Yeah,
because
yeah,
that's duality.
Probably is. And that's one there. Now this diagram is going in the direction of category theory, and we've been exploring that possibility. So that's and this is another version of the same diagram in more diagrammatic form.
Can you switch to that last slide? What was the Z?
Oh yeah,
Z
I've just replaced these by algebraic symbols, the
okay.
properties.
Yeah. Okay.
I also do that. I mean, I've done X, Y, and Z, and you can do 1 and 0 and and 1, 0, 1, and you can do all kinds of representations. But this one here, now this is the algebra of the group. This is the full algebra now. Let's see the algebra. Space, that's space with vector, pseudo-vector, pseudo-scalar, and scalar. That's the full algebra of the space, plus and minus, of course. Quaternion with its 1, pseudo-scalar with its 1, and scalar with its 1. And a nice way of representing this is 2 spaces, because the 3 last quantities you can connect together as simply one equivalent to one ijk vector. Upright is vector in mine, italic is quaternion. So I've got two vectors now. And now let's write the full group table out, 64 elements. Exactly the same as the 5 gamma matrices of the Dirac equation. If you multiply out the gamma matrix, you get exactly this. And these can be matched turn by turn with the gamma matrices. And you can also do it as a double space one, like so. What I'm saying here, if you look at these, each row on this table, on this half and each row on that half, represents a set of generators of the 64 gamma matrices. So with a group you only need generators to provide the whole group, you don't need every element. So the whole group is produced in a set of generators. Really we should complexify them to make it work totally, but essentially this is a group of generators for this 5, and this 5 is, and this 5 is, and this 5 is, and this 5 is. And they're all generators of that 64-part algebra. And
you generate the Lorentz group.
Not the Lorentz group, the 64-part group. You get the Dirac group, if you like. I don't know what it's
Dirac
called.
group, that's right.
Yeah, Dirac group. And this is very important. I want you to look at this very carefully. If you look at, let's just look at the first line. If you look at the first line, you've got 3 vector quantities. And these 3 vector quantities are multiplied by the same quantity, red I. So those 3 are perfectly symmetrical as they were before in this set of generators. However, if you look at the red quantities, the I, the K and the J, you see they're associated with different things. This one is scalar association, this one is pseudoscalar, and this one a vector. This is why the symmetry of charge is broken. It's because of the algebraic representation. And it's broken in exactly that way. And that's what gives us our characteristic SU3, SU2 and so on. So, the symmetry of 8 algebraic units is broken. There's an extraordinarily simple answer. It's not broken globally at all, but it is broken locally. Every time we create a local state, particle or whatever, or even any kind of local state, we break the symmetry. If we create a local state, something new and limited, it means combining all the parameters mathematically. And you take the tensor product of 4 algebras, which is what we get for that group. This is the reason why we've got a space-time connection. But we've also got other connections between the parameters at the same time. Space-time connection is brilliant, but it's not the only one. There are, when I was trying to understand the Dirac algebra in gamma terms, I found that it wasn't a pure 4 vector. There was something else, because the time was multiplied by gamma naught, and the space was multiplied by gamma 1, gamma 2, gamma 3. So it wasn't a pure 4 vector. It was something on top of it. So, okay. So I was saying, I've just explained this. It breaks in exactly the way we want, because the pseudoscalar time gives it the characteristics of the weak interaction, 2, I, switching up and down. Strong interaction, vector, switching between the 3. And electric scalar, not affected. And that's another way of representing it. In fact, you map the 3 charges onto the other 5 parameters to get the 5-fold symmetry broken object. And I say in doing that we create new quantities that never existed. We started with time, space, mass and charge, and in doing this we're creating new quantities. We're creating energy by doing that, we're creating momentum by doing that, and we're creating rest mass by doing that.
That's the discrete mass, the rest mass.
The discrete mass. Yeah. And so the physical natures of energy, momentum and rest mass are determined by their algebraic units. They're not, When I say E, P and M, the E and P are just scalar values. The real things are the quaternions and the vector quantities with which they're multiplied. Now if you bundle all this lot together, this is one of the sets of generators, and then you put scalar values after it, then I'm saying when you create a local state, you can only choose such values of those. You can't choose any values of those. You can only choose such values of those that this squares to 0. You can't choose any values you want. So when we create locality out of universality, it takes in place in such a way that totality is 0 by both multiplication and addition. I'll explain that later. So we can identify this as Einstein's relativistic energy equation, which of course is when the C's are included like that. But in particle physics we generally ignore C and H. And the Dirac equation now simply quantizes this. It uses the fact that these things, these are really differentials in space and time, and puts that as a differential and then finds something in which it will differentiate. And also all this business about having 4 problems, spin up, spin downs, antifermion, spin up, antifermions, all you've got to do is switch around the E and P terms, or the operators. Plus and minus, that's all there is. There's no, in all the textbooks I see, it's a horrible mess. They never actually say it's so easy as to do as that. If you take the top bracket as the defined state, then all the others follow with it. And by the way, why does the state have 4 terms when we know it's really a fermion spin up? Well, the reason is that the others are the vacuum terms which go with it. And it doesn't matter whether it's free or bound, it will still look the same. Now I'm saying nilpotency is equivalent to creating a point charge source or charge singularity in 3-dimensional space. We combine 2 spaces, the blue one and the red one, space and anti-space, to effectively cancel and create a region in which the spatial extent is 0. That's the point particle, or point-like particle, one might say. It's, you know, it depends what state the particle is in. Through the nilpotent condition, the 2 spaces share dual information. It's just differently organised in each. And I've shown that you can actually get the same information from the red and from the blue. It's amazing. They're not different, they're not separated. And the observed space becomes multiply connected because it's acting as 2. And this is why we get spin, half, Berry phase and all these things that involve the factor 2. Even, by the way, half mv squared. And even half base times height is all based on that same factor 2. That comes from this. So let's go back to where we were, and let's do it the way it's normally done. We start with something and then we apply canonical quantization. So I've got d by dt and I've got del here and I've got p there. And the thing is that you have to find what phase factor will give you back your quantity. And the only one that will is this.
It's an eigenvalue.
Yeah, it's eigenvalue. And so, also, we can represent this as operators. These can be represented as operators, so it looks the same. And then this is very interesting, because I have never seen anything that gave me a clear-cut answer to the 4 components of the Dirac free particle wave function. There we are, that's it. However, I've actually not gone far enough. What we can do, I've not included something I should have done. We can switch the variation in this phase into the variation in this. So instead, we can have the same phase, say this one, and then we just change these.
Operator, you said it switched its variation.
The operator's already switched. but I can switch that as well.
Okay.
And actually, I don't think. I'll come back to that. I haven't got the slide for it. But we have one operator, but basically you should only have one phase term here. This should be exactly the same. And that makes it so easy to do once you've got one phase term. You've only got to do one calculation for anything, ever. And you just get the perfect set of stuff. I was trying to find where that is. It's not in here. We've got one operator, 4 amplitude terms and 4 phase factors. But I can change it so we've got the amplitudes are changed and the phase factor is just 1.
Right.
And that's the thing that you've got to differentiate, and that's the difficulty. Now, the thing that one of the theories that really has always interested me is the single fermion theory. It's all called single electron theory, because that's a really great idea, and it really works well. And I think, I'm not sure who first came up with it. I think it was
Wheeler.
possibly Wheeler. Yeah, okay. I think it's a great idea, and the arguments against it don't work at all. I can show that. If we do that, we only ever perform localization once. And I kind of believe that that's true for anything. It doesn't have to be quantum. Even classical equations, we don't perform it twice, only once. We only ever deal with one thing at a time. That's all we can deal with. I had a colleague who was determined to get a 2-particle interactions out of the Dirac equation and spent 20 or 30 years trying to do it and couldn't. And that's because you can't. You can only do one thing at a time. And that's because you can only localize once. Localization is a single operation. And then you watch it change over time. Right, okay. Now this is important. Amplitude is always nilpotent. Every time it squares to 0. It's true when the particle isn't free but constrained. I've only done free particle, but I can do it constrained as well. And then you get a different phase term because you need a different phase term if it's constrained. But you still get the same result of nilpotency squared into 0. So this condition in effect substitutes the Dirac equation and implies that the fundamental expression is an operator rather than an equation. You don't actually need the equation at all, you just need the operator. The operator codes for all possible states and time variations. And you don't even need all the operator. You don't need the 4 terms, you only need 1. And you don't even need the 3 terms because the mass term is worked out from the other 2. You need 2/3 of a quarter of an operator. You don't need anything else, in principle. So each of these sets of generators of this algebra, 12 exit, produces a set of mathematical equivalents to the gamma matrices. So each of the set produces a new combination parameter, and the total is basically angular momentum. That's what that object is. It's an angular momentum operator. That's what that nilpotent really is. And this is how we create a local state from the non-local universe. And the 2 parts look the same. That's why it's nilpotent. You've got the operator, the particle, whatever it is, the EP and N, and then you've got the reverse, which is like taking that out of nothing, so it's minus that. So that's why it squares to 0. So the universe looks like the particle. In reverse, it's like taking the particle inside out. And that's where you get all the factors of 2 from, again. And so quantum mechanics and quantum field theory, this extends to quantum field theory. Every fermion determines its own universe. I think I'll just leave that. I've listed a lot of consequences, and unfortunately I can't go through all of these, it would take forever. But all these are true, and they're completely obvious once you do a calculation. You don't need second quantization. You get a part. The reason why all these quantities have Coulomb potentials is because the polar form of the Dirac equation, where you're centralizing it, the source it has a Coulomb requires a Coulomb term to get nilpotency. Won't square to 0 without it. So if you insist on squaring to 0, you can't do it without a Coulomb term. Local, non-local, dead obvious. Vacuum, dead obvious. Only one term needed. Redundancy of everything except for the operator. And here's some other things. No matter antimatter, there is, but matter is in one space and antimatter in the other. One's in out space, one's in vacuum space. The alternative space. 3 types of boson with scalar wave functions, and I've predicted a CP violation in graphene, which a man at some university in the north of England promised to do sometime, to do the experiment. We've got an immediate structure for baryons, and what happens is this thing switches from this to this to this. All 3 aren't valid at once, you only have one of these.
Is that the suitable way?
Zeta-Bewegung is really the weak interaction rather than the strong interaction, but that does create mass.
Yes, okay.
So the demand massless gluons are massive baryons because of Zeta-Bewegung, because Zeta-Bewegung is switching of this is Zeta-Bewegung, and so you will get you can't have left-handed and right-handed at the same time without mass. But you have to have left-handed and right-handed at the same time with this, otherwise you don't get the balance of the quantities. So the baryon spin is not entirely due to valence quarks. That's obvious from it. And gluon exchange is actually a Higgs-related process. And any of you are welcome to nominate me for the Clay Prize, which is quite a lot of money, because the answer to that question has got a prize for it. Linear potential for strong. The reason why you get linear potential is you've got constant change in momentum. Does anybody actually know what the strong force actually is inside a proton? It's a very amusing answer. There is an exact, well not exact, but a close value to something familiar for the strong force. Just thought I'd ask. It's actually 1 ton weight. The strong force is the same for all systems of baryons inside, and it's actually a ton weight as it happens.
Imperial or metric?
Well, it doesn't make much difference, does it? It's an approximation, so it won't make any difference. It's only 3% difference between them, isn't it? Fermions are their own vacuum bosons and vice versa. You get a natural supersymmetry between them. You don't need actual supersymmetry. Weak sources are dipolar. And the weak sources being dipolar means that you can do the weak interaction calculation by using something that a dipole would do. And okay, let's just carry on. So I'm saying locality and non-locality aren't different concepts, they're the same thing. Locality in one place means non-locality somewhere else, everywhere else. The 2 descriptions are the same process. And you can work out the electric strong and weak interaction determined by the vacua that they create. So Pauli exclusion actually creates the local Coulomb term. That's interesting. Okay, I'm saying superposition of spinor terms creates dipolar source for weak interaction, and so the solution for that is a harmonic oscillator. And that's what the weak interaction is, a harmonic oscillator. And I've found that you can only have 3 solutions. And there's no infrared divergence, no hole in the mass shell. A few things about gravity, which is a little bit apart from this. The electric strong and weak, the local is real and the vacuum is virtual. Gravity, I think the vacuum is real and the local is virtual. The local being the inertia. And I've done quite a lot on this, but I can't do most of it. But I did get granularification at the Planck mass. But I did that by, using a quark theory of a particular kind. I've proposed a test for the electric interaction, fine structure constant, that at 14 TeV, the maximum energy of the LHC, you get 1 over 118 and not 1 over 125 as the current ideas would suggest. Anyway, I'll not go much into that. Now I can't do this, I haven't got the time, but this is what the rewrite structure is. So can I just go through this very quickly? I'm going through this, it's a sort of computerized version of doing this. I realise that it's going to take too long to do this, so I'm not going to do this.
You've got maybe 5 minutes.
Yeah, I know, I've not got very little time for it. The rewrite structure produces algebras, and with Sydney I did a one-line program. This is the one line here. This one, do.
That's the operating line.
Yeah, that's the only line that matters. The rest is just setting up.
Yeah.
And Mathematical able to do a line which created all the states. That's a diagrammatic version. Produces an infinite sequence. Mathematics comes out of it to some extent as well as logic. Goes on to infinity. Entropy is due to the fact that entropy is just a number, it doesn't have any units, and it's just doubling at each stage, the number of states. Stops at 4 because it requires zero totality and perfect symmetry, and that's the only place you can get that. Now, I tried having a go, see if we could do this with genetics, and with a biology colleague, Vanessa Hill, who's an ANPA member, we did it. We got platonic solids to do it as well, and we got the five-fold structure. Oh, this amuses me. The five-fold structure is like branching off, branching off, branching off, and my favourite illustration of that is a monkey puzzle, which does exactly that. I won't bother with that. And we could use a dodecahedron or an icosahedron on the outside. And I've worked with Peter Marshall on many things. It's the late Peter Marshall. And I'm saying that this doesn't require relativity. This equation's true in classical as well. It's just that we think m's dominant in classical. I'll go past that. Because I want to just mention this. Because if we look at the 64 units, we can express them as particles, and there's two ways of doing it. We can either say we've got 64 units, 48 are particles, 16 is space-time without any particles, or space without any particles. In the second case, we can take 60 of the units, we ignore the complex units, which gives us 48 fermions and 12 non-3D bosons. And I'm not quite sure why you get two lots of it, but you do. I think this is what nature quite frequently does. Those are what I've done there. And if you had a one fermion theory, you could think of the fermion as switching between all those. And that's where it gets its masses from, as the switching requires masses. Not that you can do it switching. It's a big table that incorporates many, many things. I'll just go past all this. This was the genetic code. This was doing it using all the codons. You have first base, second base, third base, and you use those things, and you get 64 codons. And it works. There's only one or two. There's only one exception in the whole of it, and that's arginine and serine, I think. And arginine is just, but that's only in one species. It's probably not. It's probably a crossover in one species. And that's if you represent it on a super platonic solid, what is it, icosahedron, then this is the four parts that you put together to get it. You can get the five-fold symmetry, which is the nilpotent. I think convergent evolution is evidence for this, because some structures, you get the same structures even though the ingredients are different. This is just saying what next. We're going to do category theory. Obvious in some things here. Sydney's, got a presentation with some category theory in. We've got a paper ready for Prague next year, and it was ready for 2020. Cellular automata, this is a big development. I can talk about that privately, but that's a paper for November. Sydney's, and I, we worked on the logical and computer representations. And laws of form, that comes into the logical and computer work. Okay, thank you.
Also from Zoom. Shall we ask Zoom people who are
Zoom
at disadvantage? Okay, John.
Can't
You're on
hear.
mute.
Hi. You're talking about the graph algebra being kind of the vectors appear there both with time vector appears with gamma 0 and the others appear with gamma 1, gamma 2, gamma 3. So these things are not vectors, really, because as you said.
No, gammas aren't vectors, but they contain vectors.
No, they're not. Obviously not. No, but you said that so there's an addition there. So you're looking at a kind of a superposition of something which is a vector, a 4 vector, and something which has the gamma matrices.
Oh yes, that's right. Yeah, I've always thought they fudged it in textbooks because they call it a 4 vector and it isn't.
Yeah, it's not. It isn't a 4 vector. You know, it's certainly not a 4 vector because the vectors, the kind of thing we call vectors, are not vectors. But how do you see? You're right. It is fudged in the textbook. But could you expand on that and say how do you see that?
Have we got a pen or something here? I'm saying the way I do these things. I'll bring this round. I'll turn it round to the audience at the moment.
Or stop sharing and then.
Stop sharing your
Can you
screen.
just knock it off?
Then I'll see a big picture of the screen. Yeah, that's.
Where does this go? Put this
Turn it down.
Put this here, I'll turn it round to the audience. Sean John.
There we are. Got you. Brilliant.
Yeah. Now this is gamma naught is over here. Gamma 1, 2, 3.
Out of focus.
Then we move it back to the board.
Maybe it's about, yeah.
No, it's still out of focus.
It's that thing that's out of focus.
Your hands in perfect focus, but the board isn't.
If I move my hand gradually out towards the board.
Oh, bring that right up to the board then.
We've got it. It's because there's
I
something.
got it now, we got it.
Contract, yeah.
Okay.
It's working. Write more on the board, a big cross or something, or
Yeah.
Yeah,
Write
okay.
something thick. Yeah, I think it's just because those lines are a bit up thin.
contract.
That pseudo scalar there times quaternion K and a curly line under for quaternion.
Yeah, got it.
This one here is I quaternion and I vector. I quaternion and J vector, and I quaternion and K vector. These are multivariate vectors, the quaternion-like vectors. So the thing is that this is not corresponding to this multiplied by something, as it would be if it was a 4 vector, because you've got K multiplying this and I multiplying these. And that's why I say they fudge it in the textbooks.
Yeah, they do.
And I was bamboozled by that for quite a while. But it is fudged.
It is fudged. Yeah, okay, good. No,
You're happy with that?
Yeah. I hope we can have a chat first. I think we're going to come down.
Yeah, if you come down, we can chat.
Yeah, great.
So, are we doing for questions?
Yeah.
There is a question
Sahu has a
from
question.
Sahu.
One question over here in Sydney about the categorification, the periodic table, that picture that you showed, the square of opposition.
Yeah.
What are the morphisms exactly?
Well,
for that?
if you look at, if you remember those things where I had crossovers and arrows.
Yes.
Yeah. Well, you can. It's between each type and each other type both ways.
Yes, they're double sided.
Yeah. So that can become a category theory diagram.
I wonder what the interpretation of that arrow is. Like, let's say from M to C. What does that mean, or is that just a abstract?
We're working on it.
We're
We're gonna reveal it.
We're working on it.
Don't reveal it too early.
No. It'll come out in the wash.
You don't want to be scooped.
Have you thought, Peter, about this idea of considering only one localized object at a time and all other objects being subsumed into the non-local state?
Yeah.
Could it be the kernel of an approach to solving multi-body dynamics problems?
I think so. I think so.
Yeah.
And it's also one thing I didn't get onto was the renormalization group, because the renormalization group does that for you to some extent.
Yeah.
Because you just have the same structures but different things.
Yeah.
And the renormalization group, it comes from the P term.
Yeah.
The P term is the only term that matters because that splits up into many things when you've got many components, and it becomes one when you've got them all. And the P term is what makes the renormalisation group possible. Yeah.
So it's a sum over possible, possible not trajectories maybe, or possible divisions into subcomponents.
I haven't looked into the types of quantum mechanics, like sum over histories and so on so much.
Sorry, we have a hand on Zoom. That's Albert.
Just ask him unmute. Yeah, no, he's unmute. Yeah, Albert, go ahead.
Okay.
Yeah, go ahead.
Yeah.
I have a general question to your formalism. I doubt, or I want to ask if the formalism is able to cover the next lower level in physics. For instance, you have a way to
If you mean if there's a lower level which the formalism can cover, well, it isn't covered at the moment because it seems to be ideally suited to this level. Now, I don't know whether it could if there were such a lower level. I'd have to investigate.
Yeah, but because if the electron, and that's my opinion, fermions have internal structure, this has to be also treated by theory in some way.
If it has, but I have no reason to believe it is structured in that way. I have no reason to believe. If other people have, then they can put forward their ideas. But I haven't got any reason, so that's why I haven't investigated that.
For instance, another example which I would like to mention is that Pauli exclusion is treated as a principle, which means it's not explained. But the Pauli exclusion has also physical causes. There's something in an elementary particle which causes that this exclusion happens. Yes?
What I'm saying is Pauli exclusion is obvious from this theory because each nilpotent is unique, and it can only square with its own type. And if it finds its own type, they're both going to disappear into zero. And so it can't exist.
You effectively relate Pauli exclusion to the annihilation and destruction operators for fermions.
Indeed.
Yeah.
But there must be a physical mechanism.
Well, it is annihilation, it is the weak interaction. There is a physical mechanism, the weak interaction, which destroys and creates fermions. So, I mean, you go ahead if you think that you should do it that way, but as far as I can see, I don't need to do it that way. So, I can actually get it done.
Okay, I mean, it is good thing that you can't come to blows, because...
We're not coming to blows. We're not arguing.
Well, so why are we meeting here if we are not arguing? Thank you very much, Peter. I'm sorry to jump in.
No, you've got to keep
the time. We can continue later. May I suggest we have 5 minutes comfort break so people can grab tea, coffee, or go do whatever you do on Zoom. And we meet here in 5 minutes, so Dennis can give us the second part of his lecture, why universe is four-dimensional. I think it's multi-dimensional, but we can discuss it later. Okay, so 5 minutes, not more.
Andrew, can I just pull this thing out?
Which thing? Andrew.
Yes.
Andrew is not here.
Oh, can I just pull this out? Does anybody
I have no idea.
Wait, make sure you do it.
I don't know how to...